We're going to move to the next. It's Dr. Tempest from NanoFCM.
There I am. Hi, I'm Rob Tempest from NanoFCM, and I'm here to talk to you today about our instrument called the NanoAnalyzer, and really how we're utilising nanoflow cytometry for a more comprehensive assessment of, in this case, LNP quality. So just a bit of a company statement there, but really just to highlight that while I'm going to be specifically talking about LNPs in this context, we cover a whole range of really nearly any nanoparticle that's going to fall into the sort of sub-1 micron area. Traditionally, we've done a lot of work with extracellular vesicles, like is going on in the adjacent session downstairs. But really, nanomedicine's become really the largest part of our business. So when we're thinking about LNP analysis techniques, obviously you'll all be mostly aware of DLS for our sizing measurements, and using things like ribogreen assay for doing that encapsulation efficiency. Where nanoflow cytometry comes into this is one as an orthogonal technique that can also cover size distribution as well as particle concentration. But this is a particle by particle assessment. So rather than a bulk analysis you're going to get from the DLS and the ribogreen, we can see every individual particle and determine information about that. So with that in mind, we can then start to calculate things like our loading ratio, as well as actual RNA copy number per particle, and looking at that distribution. So what's actually happening in our system? Where we differ conventional flow is in a couple of ways, but what we're doing is we're loading as little as 10 microliters of sample at a time, with actually less than 1 microliter consumed in a standard acquisition. That's then pumped up and into the flow cell with a highly controlled pump, where really the different things that we're doing is we're focusing down that sample stream to a really narrow 1.4 micron stream, so we get a much more true single file movement of particles through the laser. And we've also slowed down that movement, so we get an increased dwell time of these particles in front of the laser, so we can gather more light information and fluorescent information per particle. So as they're passing through, like I say, we gather this information. You can see that sort of display that would come out of the system here. Really what is of interest is down the left-hand side, or what we call our event burst traces. So each line you can see coming through there is a simultaneous measurement of both side scatter, which we use as a basis for sizing and concentration, as well as fluorescence in 2 channels, and the height of those lines being relative to the intensity of that signal. So when we're looking at LNP characterization, what it means we can do is get that single particle sizing and particle concentration. You can see a typical sort of size distribution graph below there. So rather than just that bulk analysis you might see from the DLS, that's individual particles, each of which can have its own data exported for every single particle analysed. We can then build on that with, and these are the sort of more unique, the more novel data points that we can provide, is this loading ratio, where we can show the percentage of loaded particles versus those that are empty, as well as the concentration and size of those subpopulations within the whole sample. And then we can also look at the quantity of that loaded material, so the mRNA copy per LNP. And you can see here that sort of frequency distribution where we're showing the copy number across the whole sample. This is only really utilising the first fluorescence channel. We still have a second fluorescence channel to look at other things like surface ligands with antibody staining or secondary cargoes that you might be interested in. So just to really illustrate how that's done with this example, you can see this is for an empty LNP, but basically on the x-axis we've got our side scatter related to the size, and on the y-axis we've got our mRNA label. So you can see here that we've got a large population that has no positivity for this fluorescence for the mRNA label. This has been done with a range of dyes called the Cyto dyes, which are membrane-permeable nucleic acid stains. Whereas when we look at the loaded particles, we can now see this big population of mRNA loaded with mRNA with the dye. So really now we can determine that we've got a 90% loading ratio, as well as the overall concentration of that sample plus the concentration of each of those subpopulations. And similarly with size, we can describe that for each of them. Again, we still have the option then to look at additional targets on that, such as surface antigens and secondary cargo. So Now we're going to switch to how we do the sort of quantification of the mRNA. So you can see now that instead of gating across the y-axis as before, we're now gating on the x-axis. So in the previous example, we were using a side scatter trigger. So we were looking at all particles that were large enough to generate side scatter, which for our system is anything over 40 nanometers up to 1,000 nanometers. By switching to a fluorescent trigger, the instrument's actually sensitive enough to see individual copies of mRNA in solution. So you can see that here in blue, where we actually get a uniform intensity for those individual copies. So in this case, this is sort of just for illustrative purposes, but say if that's 200 intensity, we can then use that as a basis that when we get an LNP with 1,000 intensity, we have 5 copies of the mRNA in that particle. And that allows us to generate these frequency distributions where we look at the copy number per particle. So I kind of want to go through that more in the scope of a couple of case studies, which are some collaborations that we've been lucky enough to be part of quite recently. So the first one was working with a company, Vax Equity, and what they were interested in is self-amplifying RNA. So these were self-amplifying RNA that is capable of being put into these particles, and then it results in, because it can self-amplify, as the name suggests, you get an increased cellular mRNA and increased protein expression. But as you can see here, it results in a much larger molecule than the standard mRNA cargo you might have seen. So really wanted to look further into that. So you can see here what I'm really going to focus on is going to be 2 different formulations, 2 different ionizable lipids, siRNA cargo that are carrying and really looking at a series of NP ratios, so the ratio of that lipid to the nucleic acid. So by looking at traditional characterization by DLS, we can see here no real strong trend between the NP ratio and the size of the particles that we're looking at, or the PDI. Similarly with NanoFCM, we see a very similar trend. We see some slight fluctuations, but really no big differences in the size. We see a slightly lower size than the DLS, coming down to the single particle level that we're characterizing these samples on. When we then look at the ribogreen assay, again, you can see some slight fluctuation, but no significant differences in these across these NP ratio series. And again, when we then use our system to calculate the encapsulation efficiency using that ratio of the unencapsulated individual mRNA measurements to those within the particles, a very similar story where we don't see any difference. We can then go further, though, into this comprehensive analysis. So using that sort of example I showed you earlier in the bottom left of empty versus loaded using this Cyto dye, we can now start to see much more interesting changes in our samples. So here we can see that as we increase the NP ratio, we get a much lower proportion of loaded LNPs within our sample. And almost just as important, or maybe more important in some cases, a larger proportion of unloaded LNPs. So you could look at that in a couple of ways. One might be that here we're seeing wasted reagents, large excess lipid that's being added that's unnecessary. And you might also look at it as a contaminant, additional particles in there that aren't carrying our payload of interest. The next collaboration we've done that follows on from this is with PNI. Again, this is looking at an NP ratio, and now we're back to our sort of mRNA LNP. So these are all samples that were made with the Ignite, and really looking at differences between NP ratio again. So here, again, you can see the conventional, they're all within the sort of size range we're expecting, and when we measured them by nanoflow, again, we saw very similar sizes. Here we've separated them into loaded and unloaded, because you might say there is a slight trend there that the loaded LNPs are actually reducing in size as you change that NP ratio. We can then look at the encapsulation efficiency again with ribogreen and see maybe a slight increase as we go up the NP ratio, but really nothing too significant. And actually, in contrast with the last example of the sRNA, when we're looking at the loaded versus empties, we can see a slight increase in empties as we increase the NP ratio, but nothing as significant as we saw in the previous example. That's where we can then go further into this RNA quantity analysis. So you can see we've taken the 2 sort of extreme examples there of the lowest and the highest ratio that we looked at. And you can already see from the dot plot and that sort of blue dashed lines there just to illustrate this, that we have a real, in the MP4 we have a much higher spread of the amount of mRNA in those, where we have a more focused lower amount in the MP12. So when we start to graph that, you can see a really clear trend here where as we go down in the, as we go up in the ratio, sorry, we see a reduction in the median copy of our mRNA per LNP. So that kind of, you can look at it that way as thinking, great, the NP4 has the higher payload, but you can also look at it another way in that the NP4 also has a much broader distribution within its sample. So if you were more interested in a more narrow, homogeneous LNP formulation, you might think the NP12 actually falls better into this region. And then the final sort of part of this same collaboration that I'll talk about is using a comparison of different mixing methods. So these were 3 different batches prepared with either the Ignite or the manual methods of vortexing and hand mixing. So when we look at the DLS analysis, we can see an obvious change here, right, in that the vortex and the hand mixing result in a higher size of LNP versus the Ignite system. When we then look at the encapsulation efficiency, we can see that we've got a much lower encapsulation efficiency in those particles as well. So this is using those basic nanoparticle characterization techniques we've already discussed. When we then get into that more comprehensive analysis using the NanoAnalyzer, we can look at the empty versus loaded and really see, again, kind of what we'd expect from that previous data, in that we have the manual methods result in a much higher empty number of LNPs versus a much more efficient loading ratio seen in the microfluidic system. But interestingly, we don't really see a difference in the median copy per particle. So we see a lot more variation in the median copy, and actually if I go back to the previous graph, we also, with the manual mixing, we see a lot more variation in encapsulation efficiency. There's not much change here, but when taken as a whole, you can kind of see the picture of that almost the manual methods aren't resulting in the nucleic acid being introduced to the LNP as readily. So you're getting the formation of a lot more empty particles compared to the microfluidic system. So really, in kind of summary there, what we're doing is this multi-parameter LNP analysis where we're providing this orthogonal corroborative data in terms of size and encapsulation efficiency, and then we're able to add these additional novel data points to it. So we're looking at particles per milliliter expression, because it's no longer a bulk analysis technique, as well as that loaded to empty ratio. We can also quantify this loaded material, so looking at those copies per LNP, and we can also do other things like looking at cargo location, which I haven't gone into. So for example, we can see if your mRNA is externalized or internalized, which might tell you a lot of information about the efficiency of the system. So what that can do for you really is it can help you identify wasted reagents and reduce those sort of expenditures, as well as identifying potential contaminants, whether that's increased empty LNPs or that's increased free mRNA in the system, so a lower encapsulation efficiency. When it comes to refining the formulations as well, it helps you make that sort of decision where you can decide whether you're more interested in high yield or homogeneity. So giving you all those data points to make those decisions. So I just want to say a thank you to our collaborators and to our research team led by Ben Peacock, who's allowed me to take the credit for this. And then really just some contact information if anyone would like to reach out.